Hi, I'm Anelise, and I'm here to tell you about a new toolbox for capturing attention data. Human attention provides insight into what aspects of an image are most relevant or engaging. For example, if I had a lot of data about where on an image people tended to look, I could train an automatic cropping system that preserved the most relevant parts of an image. If I knew what aspects of a graphic design were most important, I could do design retargeting. If I could measure attention at multiple scales, that could give me insight into how people explore complex images, like data visualizations. And if I knew where people tended to look at different viewing durations, that would help me prioritize content to display or render. But despite being so valuable, human attention has a drawback, and that is that it's historically been difficult to collect at scale. Say I wanted to gather attention on this image. The typical way to do it is to bring someone into the lab and then track their eyes using dedicated hardware. I would measure the points on the image that they looked at, and then by combining these gaze points over many study participants and blurring them, I could create an attention heat map. In this heat map, higher values correspond to regions of the image that people look at more frequently or longer. However, this method of collecting attention does not scale. Bringing subjects into lab is time-intensive and, during a global pandemic, probably not possible. So in this work, we present TurkEyes, a toolbox of 4 interfaces for gathering attention data using just a laptop or mobile phone without eye tracking. Instead, we make use of interaction methodologies that are correlated with attention. With zoom maps, participants use the pinch zoom gesture on a mobile phone to explore an image at multiple scales. With code charts, participants self-report where they gazed using a grid of 3-letter codes. Important Knots lets participants paint over regions of a design that they consider important. And finally, Bubble View requires participants to click to unblur small bubble regions of a blurred image. We do a deep dive on these interfaces to develop guidelines for how and when to use them to capture attention. So let's introduce the interfaces. Zoom-based interfaces use a viewer's zoom patterns as a signal of interest in regions that are viewed or zoomed. Previous work has explored the correlation between eye movements and the zoomable viewport of a mobile phone, and has even proposed using viewport data to measure interest in an interface, or even to create an attention heat map over a web page. However, as far as we know, Zoom Maps is the first general interface for creating attention heat maps on images using Zoom. Here's a demonstration of how the interface works. Participants are sent to a landing page that contains a QR code and a URL that they can use to open an image gallery in their mobile browser. They can then explore the images in a mobile image gallery using the familiar pan-zoom gesture. We can then convert the zoomed viewport data into an attention heat map as follows. For each pixel, we take the average zoom level over the viewing duration, where the zoom level is defined as the full image area over the zoomed area. So a pixel that is viewed up close, like pixel B, will have a higher heat map value than one that is only viewed while zoomed out, like pixel A. Thus, we get a measure of where the viewer spent the most time looking in the most detail. We can then combine the viewport data gathered from multiple individuals to obtain a zoom map. Moving on, self-reporting interfaces like code charts show an image for a limited time and ask the viewer to report where they were looking using a visual guide. Our implementation of code charts is based on an interface presented by Rudoy et al. Here's a task flow diagram for the code charts interface. First, an image appears for a specific duration, usually a few seconds. Once the image disappears, it is replaced by a code chart, a jittered grid of 3-character codes. Once the code chart disappears, the subject writes down the code they remember seeing when the image vanished, which locates where they were looking at that time. This video shows the interface in real time. The code chart goes by really fast, and that's on purpose. We want to give people enough time to read a code, but not enough time that their eyes wander. After we've collected gaze points from multiple participants, we again convert that data into an attention heat map by blurring the gaze points with a Gaussian, similarly to how eye fixations are processed. Next, annotation interfaces allow users to explicitly segment regions that they think are important. One example is the Label Me interface, used for collecting semantic segmentation labels. Important Knots refers to the interface O'Donovan et al. Used for collecting importance annotations on graphic designs. Participants are presented with a series of images one at a time and asked to annotate the most important regions. We don't define what should be considered important. Even though there is considerable variability in the annotations obtained from individual subjects, by averaging over many study participants, we can obtain a surprisingly consistent measure of importance. And this technique also works for natural images, although the segmentations might not be as clean. Finally, cursor-based interfaces leverage correlations between mouse movements and eye movements, often by incentivizing the viewer to click or hover to explore points of interest. For example, the moving window methodology, like Bubble View or Salicon, reveals portions of an otherwise obscured image depending on where the user places the cursor. Participants are asked to explore one image at a time, using their mouse cursor to click and deblur small regions of an image. Heat map generation is then very similar to code charts. We blur the collected mouse points to create a heat map. Now, I've just thrown a lot of information at you, so you might be wondering, which tool is best? Which one should I be using? To try to answer that question, we ran experiments on Mechanical Turk. We gathered data on a variety of stimuli types like natural images, infographics, visualizations, to determine what insights about attention we could gather from each tool. Here's what we found. One thing we realized is that not all interfaces work equally well with each type of stimuli. For example, zoom maps works uniquely well with large multi-scale stimuli because of the really natural support for panning and zooming. While you can use important knots with natural images, it's really best suited for graphic designs. On the other hand, all of the images that we studied support graphic designs, as you can see in the resume on the right. And finally, although we did not try this in our experiments, code charts can be used for videos by replacing the image with a short video clip. Cost is another important factor that we considered. The cost of data collection with each interface really came down to two things. How much data does it collect per participant, and how much work is it to use the interface? Out of the interfaces we studied, Bubble View was the cheapest. One reason is that Bubble View gives a relatively high amount of data per viewer, as you can see in the image on the right. We get about 15 clicks per viewer, which means we need about 15 viewers per image to get consistent data. The next cheapest is zoom maps. We need slightly more people, around 20, to get consistent zoom maps data for an image. Code charts is significantly more expensive than either of the two previous interfaces. So why is that? Whereas with Bubble View, we get many attention points per participant, for code charts, we only get one. That means that we need a lot more code charts participants to get a consistent heat map, around 50. Finally, important knots is the most expensive interface. Although it requires fewer people than code charts, they need to do the additional work of actually segmenting the elements in the image, which drives up the price. We also computed similarity to eye movements by collecting data for all of our interfaces on 35 images from the CAT 2000's eye tracking dataset. We computed the Pearson's correlation coefficient between the heat maps generated by our interfaces and the ground truth attention heat maps. We see that code charts best approximates eye movements, accounting for 88% of human consistency. It's followed by Bubble View and zoom maps, and important knots, unsurprisingly, is least similar to eye movements. This figure shows some qualitative similarities and differences between the interfaces. Code charts best approximates human eye movements. It shows things like exploration patterns or single fixations resulting from exploration, which is characteristic of eye movements. Eye movements, code charts, and Bubble View fall on certain regions only, like faces, hands, and points of contact, basically salient points in the image. Zoom maps occasionally overfocuses on distant background elements, such as the tent in the second row, and in general it's a more coarse approximation of attention. Important knots segment semantically important elements. It often focuses on a single central object, and it in general highlights large portions of the image. So what might account for these differences in how well the interfaces approximate eye movements? Our interfaces can be organized on an intentionality scale, based on the degree to which they measure saliency, which is more spontaneous, or importance, which is more intentional. Saliency is a bottom-up measure of what parts of an image are most attention-grabbing, whereas importance is a top-down measure of which elements in an image are most relevant. Intuitively, you can think of saliency as like when you're scrolling through Instagram and images are popping out at you. Whereas you can think of importance as more like when you're annotating your textbook and you're actually reflecting on the content and then annotating it somehow. We think that an interface's place on the saliency importance continuum is a function of its intentionality. Eye movements capture saliency because they require no explicit user interaction. Code charts is next because it doesn't distort the image or require user interaction while viewing the image. Bubble view still captures image locations that draw people's attention, but it's more intentional because it slows down viewing time, distorts the image, and requires people to click to explore areas of interest. Zoom maps requires the user to interact with the image to gather attention data, but it does use a familiar, more second-nature mechanism. Finally, importance measures importance instead of saliency. Participants are given ample time to consider the image before they annotate anything, and they're asked to select regions, not gaze points that they find important for understanding. These examples demonstrate some of the similarities and differences between saliency and importance by comparing the interfaces on either end of the spectrum. In the top row, you see an example where the two interfaces produce different outcomes. Code charts is more similar to eye movements, showing center bias and exploration patterns, whereas importance focuses on the objects in the scene. On the bottom row, the central objects are also the most salient, so you see more alignment between the two interfaces. That brings us back to the question, which tool should I use? And the answer is that it really does depend on your use case. Zoom Maps is great for multi-scale content. It has a natural interaction mechanism. However, it is a coarser approximation of attention. This makes it good for something like visualization debugging. While code charts can be expensive, it's a good approximation of eye tracking, especially at precise viewing durations, which makes it ideal for an application like gradual rendering. Importance produces clean segmentations, and it's really well suited for graphic design elements, which makes it ideal for graphic design retargeting. And while Bubble View can distort the stimuli in the viewing experience, it does approximate eye tracking well, and it's cheap, which makes it great for something like training a machine learning model to do automatic cropping. If you have your own ideas for projects that require attention data, you can use our toolbox to help you collect it. The interface code, data, and demos are available on our website. Thank you for your attention.